Hello all, welcome to the lecture 16 part A. In this lecture, in this discussion, we are going to discuss tree-structured regression. So we will, in the tree-structured regression, we are going to have y as a function of x plus epsilon, where we do not know what is the functional form f. This functional form f is unknown. Okay. Now obviously our objective is to estimate or learn the function f. Okay, so that is our objective. And like GP regression, tree structured regression is also a non-parametric regression method. Okay, so because remember that what is our model? Y is function of x plus epsilon, and GP regression also tries to estimate this f, unknown f, and tree structure regression also tries to estimate that f. But the methodology is very different than GP regression. Let us see how tree structured regression works. The tree structured method for regression task is based on the partition of the input space into separate region and with constant response for each region. So I'll talk about it, more about it. So typically what happens that you have y equal to f of x plus epsilon, right? And x belongs to some space, maybe some x1 or x0 to say x big M. And then what you do, you partition it into different part, the x, okay, and then for each partition you come up with the estimate for y. And if so, basically you want to say f of hat x plus epsilon, and in each part you come up with a response, a constant response. That is what it is doing. So ci, or here cm is any of the ith value, here it should be m. Cm represents the constant response for region M, Rm, where Ix is, if the x belongs to Rm, then I will take it as 1, otherwise I will take it as 0. And M represents the number of terminal nodes and is an important parameter of the tree models. We will talk about it. If we consider square error loss function, then the best option for Cm is the average response values of yi in the region Rm. Okay, the feature space is partitioned into regions R1, R2, Rm. Using a greedy algorithm, the number of regions which partition the predictor space is essential to the algorithm. Okay, so let me give you an idea about how this tree structured algorithm works. So suppose you have one x, okay, and one y. Just to understand this, and suppose these are the points. So some sort of, now what I will do, let me just take a different color. Maybe I'll take blue. So I'll just partition it into different partition, and then here, a bunch of partition I will take. Okay, here I am partitioning the x, and now in this partition, these are the points. What is the average of y of these points? Somewhere here. Okay, so this is my C1. In this partition, so this is R1 and this is C1. This is R2. In R2, these are the points. So, and what is the average of these points of y? This is my R2. In this R3, this is my R3. In R4, this is the step. And in R5, this is the value. So it is like sort of create a step function. So this is the function regression. It's some sort of non-linear structure. It's get captured. The true relationship might be like this, and it is getting a kind of a step function kind of behavior is getting captured by this tree structured regression model. Okay. So here the parameter m describes the length of the tree. This defines the complexity of the solutions because, and it is very important. So here I have taken m equal to 5. Now obviously if you choose a different m, this will be like this, could be more bigger or smaller or smoother. So the smoothness will depend on value of m. Now if you choose too many m's, then it could be too jittery or too smooth. So this could be this is something you have to be careful about. An algorithm that works well is partitioning the feature space until there is a minimum threshold number of in each case of case region. Okay. So then we shorten the tree using pruning. So we do some pruning of the tree as well. You have to do typical pruning. Pruning is aided by minimization of a loss function, which is defined as follows. Okay. So how we define? So nm is the true number of the number of cases that belong to region Rm, and Cm is the average of the responses in that region. Suppose T0 denote the tree obtained without applying any pruning. Okay, without applying any pruning, it just allows you to grow the tree as much as possible with a small bean, and that's perfectly fine. And then T be the tree that's subject to pruning. Then you do some pruning that, okay, now I need to reduce the number of branches. The pruning process involves collapsing nodes T0 to build optimal tree. It has mod T nodes. So we define mean sum of squares of error as QTM 1 by nm summation yi minus cm square whole square. QMT is also known as the node impurity measure. Okay. So we can define the cost function that is minimized during ERM with the regression tree models as like this. Okay. So now you have to be a bit careful here. What is QMT? QMT is the essentially sum of squares of errors. Sums of squares of errors, right? So this is the error, you square it, sums it. So it is sort of a mean square error in the mth region. Okay. Now what it is doing is essentially multiply it by nm. So this cancels. So what you live with just summation yi cm square, then taking of this sum over all the regions. And then it is putting a penalty. This is a penalty. Okay, penalty. So this is a penalty. So alpha mod t is a penalty. So where alpha is the parameter controls the model complexity of the t, that how much model complexity you will allow. So alpha is the tuning parameter and mod t is the L1 penalty, where C alpha t is the penalized sum of squares of error. So C alpha t is the penalized sum of squares of error. Okay. For each value of alpha, you obtain a f of alpha by applying ERM, and where equation is the minimized. So many variations of the tree models are developed. One of the popular model is decision tree and random forest. Now you can be a little bit confused that typically in the machine learning literature, decision tree or random forest are typically developed for classification problem. Yes, you are right. Decision tree and random forest are generally developed for classification, binary classification or multi-class classification problems. But interestingly, decision tree and random forest can also be applied for regression as well. So the way I just showed you, so in that case, instead of using entropy or instead of using the likelihood of binary classification, you have to use the sum of squares of error. Like obviously in each node, whatever the sum of squares of error, or each region, what is the sum of squares of error, you have to appropriately calculate and then optimize it and come up with the optimal tree. Of course, if you put penalized penalty, then you will get a pruned optimal tree regression in that way. So the random forest is an ensemble learning of tree models. In decision tree, both regression and classification problem can be modeled using decision tree. If the target variables is a categorical variable with outcome values, taking values say 1, 2, 3 up to k, the only changes needed in the tree algorithm concern rules dividing the node and pruning the tree. Okay. So for regression, we consider the squared error node impurity measure QMT. Basically, this is sum of squares of error at each node or at each region. That's it. Okay. So in decision tree, in a node M representing region Rm with Nm observation, so PMK is simply average of samples in that node. The proportion of observation that belong to class K in a node M. So as I said, if you go back to the, let us go back to the, so here it is. So this is my region. This is one region. In that region, how many points are there? These points, you just take the average of those points on Y. And that is what exactly it is talking about. That is what exactly this guy is talking about. Okay. And we classify the observation of node M classes, but basically you take argmax over K, PMK, the majority class in the node M. In this, there are different measures of QMT of node impurity, such as misclassification error, Gini index, cross entropy, or deviance. The classification error rate is the proportion of the training dataset that does not belong to the common class. So epsilon equal to 1 minus max of PMK. So however, the classification error is not sensitive to tree growing. Hence, Gini index is an alternative classification error. Okay. Gini index is an alternative classification error, and this is the measure PMK into 1 minus PMK and sum over K. A measure of total variance across the K classes. How much variability you see across classes. Okay. So Gini index takes small value if all PKs are close to 0 or 1. So if all the values are close to 0 or close to 1, then Gini index will be very small. And if they are close to half, then Gini index will be very high. So you would like all the values to be either close to 0 or 1. So you you will try to reduce the Gini index. Hence Gini index is known as the measure of impurity of a node. So an alternative to the Gini index is the entropy, and which is basically PMK times log of PMK. Take the summation and take the minus. Okay, so and D will be automatically greater than equal to 0, and it's kind of obvious because PMK will be always between 0 and 1 typically for a classification problem, and that will make the log PMK negative, and PMK is a proportion, so negative negative positive, so the whole thing always D greater than equal to 0. Like Gini index, entropy also takes small values if PMKs are close to 0 or 1. So while pruning the tree, we can use any of the three methods. However, classification error rate is preferable if goal is to maximize the accuracy for the tree. Okay. So suppose here I have taken a example. Okay. So here is the x and here is the y. I have taken y equal to sort of sine x plus epsilon. This is the model I have considered. So you can see that, between minus pi, here it is minus pi and pi, it's sort of kind of goes in and with some epsilon. Okay. Now if you apply decision tree is effectively nicely capturing the relationship, non-linear, non-monotonic relationship. So decision tree is capturing non-linear and non-monotonic relationship. Okay. So the random forest presents an improvement over the decision tree. So uses the idea of bootstrap. It uses the idea of bootstrap statistics. Remember, we discussed bootstrap statistics. So random forest uses the bootstrap statistics with a tweak that addresses the multicollinearity. It's a beautiful algorithm. I think I have seen many algorithms, but random forest is one of the algorithm which is very close to my heart, and it's beautiful algorithm. Let us see what it is doing. Okay. So and it also, so first of all, the way the algorithm is structured, it automatically take care of the multicollinearity issue. Also, it performs an intrinsic feature selection. Automatically it does a feature selection. It's a beautiful algorithm. Let us see what it does. So suppose this is my data set, some bunch of xi's and some yi. Is the training data set where xi is xi1, xi2, xip. We draw capital B many bootstrap data set as training data set D. Each bootstrap dataset contain m data points out of n data points, p dash features out of p features, okay, from the D of m samples. So what it does, let me just try to explain you what is it doing. So first of all, here you have a data set. Let me try to tell you. Okay, the data set has n samples and p features. So 1, 2, 3, 4 up to n samples and p feature 1 to p. Okay, n rows p column. So first what it does, each bootstrap data set. This is my bootstrap data set. So it samples m sample out of n. So from here it draws m samples. But at the same time, it's randomly not take all the features. It's randomly take m features, p dash many features, not p, all p features. It randomly takes p many features, p dash many features. Okay, and so suppose TB is the decision tree trained on the bootstrap sample db star. Okay, now note that the tweak is we randomly sample p dash many features out of p features. So these p dash out of p many features we are randomly sampling. So m is also randomly sampling and p dash is also. So the number of rows I am sampling randomly, number of columns also I am sampling randomly. Okay, and that is a beautiful trick that I found, because when you are drawing p dash many features, that means you are dropping p minus p dash many features from the dataset, or from any model that will be developed on using this dataset. In this dataset, p minus p dash feature will not be present. P minus P dash many feature will not be present. That is an interesting feature that I found. And as a result, what will happen? So that means you are dropping those data sets, or sorry, those features. Though you are dropping those features and you're building a sub model, a nested model. So this is an interesting feature. So that is the tweak that they are doing. So if we have two trees, one is based on TB, another is TB dash. Okay, so B is, and that is based on dataset DB, and this is based on DB dash. Two trees be trained on a very, so this tree can be trained on a very different dataset, a very different set of features. It could be trained on, say, feature number 1, 2, 3, and this would be trained on completely different feature number 9, 10, 11. So they could be very different model. And then from these models, you're taking the votes and you're taking the predictions. In the final assessment, you will prefer the tree which will have a better predictive power. In this way, the two trees get decorrelated, because here maybe you are taking the feature x1, x2 and x3, whereas in here you are building the model tree based on x6, x7, x9. I'm just throwing a number. So but you can see these set of features and these set of features are completely different. So as a result, final prediction, in the final thing, the features get decorrelated and avoid the multicollinearity. So this is an interesting feature I found. So now out of B many bootstrap dataset, we train B many trees. Okay, so now I have T1 tree, T2 tree, so B many trees, where the class T, this T is called random forest, because this T is now class of all these trees. So now the class T is called random forest. So if we have test point x0, we make prediction from each tree and then choose the majority class predicted as the final prediction. So here is a example of random forest, and here is an example of decision tree kind of plotted over there, and then this is the effectively true function. The black one is the true function, this is the true function, this blue line is the decision tree, and all these sky blues are trees of random forest. Okay, So thank you very much. I hope you enjoyed this video, and in the next video we will do the hands-on. Thank you. See you in the next video.